Hello everyone, my name is Mark Shipman and this is the demo for my implementation of the AI accelerated branch and cut algorithm as part of my submission for the Shell AI Hackathon for Sustainable and Affordable Energy 2024. This is just a demo portion, so I'm not going to go through all of the details. The details are elsewhere in the submission, either in the PDF or in this PowerPoint, and there are also links for other documentation going into more details about the branch and cut algorithm and also about the AI accelerated branch and cut algorithm. I'm going to summarize the algorithms a little bit just so that you can follow the demo. So first, the branch and cut algorithm is an extension of the branch and bound algorithm. The branch and bound algorithm uses a tree to search the solution space. Each branch is defined by an upper or lower bound to the solution, and following each branch is a search to tighten or improve the bounds until the solution gets better and better. The branch and cut algorithm extends the branch and bound algorithm by also eliminating types of solutions altogether. These solutions are eliminated or cut using what's called separators. So in this diagram, there's an illustration of the branch and bound tree and then the separators. And on the right is an illustration of the separators in the standard branch and cut algorithm. The branch and cut algorithm uses separators, and the separators need to be configured. So although the branch and cut algorithm is a much smaller space and much more efficient, there is a lot of work in configuring the separators. The link to the research describing this is here below. So in my submission, I use the AI acceleration described in this research. The authors of that research have made their work publicly available in this easy-to-use module located here on GitHub. So here are the 6 steps I use to create the solution. And the steps are in 3 different groups. The first step is to define the linear program using Python standard language. The decisions, the objective function, and the constraints from the original problem statement are converted into a Python standard linear program. And so that linear program is an input into the next group of steps, building the acceleration, using the code from the repository that I just referenced. So the output of the second group of steps is a set of configured separators that we can use to train a deep learning model. And so the final step is to solve the mixed integer linear program using the standard branch and cut algorithm with the one acceleration, that the separators are configured using the deep learning model, which is much, much faster. So it prioritizes the separators in a way that is much, much more efficient than the standard branch and cut algorithm. This notebook, which is included in the submission, defines the linear program. So first, it reformats the data, and then it defines the linear program in the Python standard language. So here it's creating the variable names. Here it's creating the objective function using Python standard language, minimize the fuel cost, minimize the cost of full ownership. So here I combine insurance and maintenance together. Here the demand constraints are defined, the emissions constraint, and then the optional fuel risk constraint. And then this linear program is saved in a .mps file. So the next 3 steps, which are building the accelerator, are from the repository from the research that I showed earlier. These steps actually are long, and even though the whole process is faster than standard branch and cut, running them is still time consuming. So I'm not really going to show them in detail, but I will show you a little bit about some of the outputs and some of the commands. And so as I said before, the commands are described on this GitHub repository. So there are 3 commands that are important that I followed pretty much exactly for my submission. There's the enumeration of the separator space or the restricted space. So those 3 commands are here. That's the first one. And then the second one is explore subspace. And then the third one is get actions. So I'm going to show you a little bit of the directory structure so you can see the output of those 3 steps. So if you clone this repository, you get learning to configure separators, and there's a directory here called restricted space where all of the results of the first step are stored, and then all of the data is stored here below. You can see in the directory called data, you can see all of the models. This is not the entire space of separators. This is a sample that you use to train the model. So in this particular notebook, I'm going to show an example of training. So the training is normally a bigger intensive process, so I'm just going to show a smaller example. The batch size here is 1,000 with 500 iterations. Normally it would be much larger. Also, this is a multi-GPU machine, and I'm using multi-process to manage each training. So here you can see the 4 different GPUs. And now down below, when you monitor the GPUs, you can see the activity. And you can see there's activity on the GPUs. And so after that finishes, you can see the result in this graph just shows the cross entropy for each model on each device. Each model trained on a different segment of the data to speed up the training. And so now in the final step, we will use this notebook to use the trained model to perform the branch and cut algorithm. So first we load the model, then we load the original model with all the original constraints from the original problem statement, and then we're going to loop through the separators and pick the best ones for the final solution. So also keep in mind, because this is a demo, we're not going to go through all the separators. This is just an example of going through a few of them, a selected few. So here there are 3 types of separators: click, zero half, and Gomeroy, and you can see that it looked at the separators, it got a score for each of the separators, and in this case it picked the best one, click, and then we use that to actually solve the final solution. So in this final step, we take the best separator and we add that to the model, and then we perform standard branch and cut. So I'm using a standard branch and cut solver augmented with separators that I've chosen using the AI algorithm, which will accelerate the process. In this example, I'm just picking one separator. In reality, there's a whole process for picking separators and improving upon them and reorganizing them based upon the model. But just for the demo, I'm just going to run the one separator. And so here you can see I set a time limit to 30 seconds, so it's finished a little bit quicker, and you can see the output here as a result of using a standard called branch and cut MILP solver. So in this notebook, I'm going to talk about the last optional part of the solution, which is managing fuel uncertainty risk. Like the original problem, it will be formulated as a mixed integer linear program. For simplicity, we're just going to focus on variables that are related to fuel price uncertainty, which are the usage variables. So that will simplify the demo a little bit. And so here we specify some input variables, which are explained in the documentation. There's the risk-free short rate, there's the risk budget, and then there is an annual threshold factor, which is, in this case, is 2 times the expected price. And so that's the tail risk point. So here we're going to use optimize from SciPy, and the problem is formulated as a nonlinear constrained optimization problem. We're minimizing fuel cost. One of the constraints is the demand constraint, as was the case in the original problem. We have the additional constraint here, which is the reliability-based design optimization constraint. This constraint is the risk constraint. So in the documentation, I point out that risk is exactly the same type of constraint as reliability. In reliability-based design optimization, you can have reliability or risk as either the constraint or as the objective function, and here we have it as a constraint. Here's the solution, and in this case I set the max iterations to 1,000, so you can see that it stopped. It did not find a solution yet, but this is still a feasible solution, and the way you can tell is because the demand budget is near 0, the risk is positive, and the cost is positive, and these are both inequality constraints. So this is a feasible solution. So there is a feasible solution, but it would become more optimal if I let this run for even longer. So to summarize, we defined a linear program using Python standard language. Then we use that linear program to configure a set of separators for the cut and branch algorithm. Then we use those separators to train a deep learning model to configure and prioritize other separators. Then we use that deep learning model to accelerate the cut step in the branch and cut algorithm. Finally, we illustrated how to use reliability-based design optimization to manage the financial risk associated with fuel uncertainty by adding the market-calibrated fair value of the hedging cost as a constraint to the optimization problem. Thank you for watching. This has been Mark Shipman with Team Sinofourier, and this has been my demo for the AI-accelerated branch and cut algorithm for the Shell AI Hackathon for Sustainable and Affordable Energy 2024.